Hello and welcome to all students in this our YouTube channel. Students, we are in the topic of chemical kinetics. And students, in our last lecture, we have seen what is meant by molecularity, and in our previous lectures, we have seen what is meant by order. And if we consider a general reaction, how to determine the order for it, and sometimes experimentally, we can also determine the order of a chemical reaction. That part we have seen in our previous lectures. In our today's lecture, we are going to learn what is meant by molecularity and order, what is their difference. By comparing the similar points in this lecture, we will learn what is the difference between them. Now students, first we will consider the molecularity and we will compare it with order. Molecularity means it is the number of atoms, ions or molecules that must collide with one another simultaneously so as to result into a chemical reaction. Means it is a number of the colliding molecules or the participating molecules in the chemical reaction. And if we consider the order of a reaction, it is nothing but the sum of the powers of concentration terms on which the rate of reaction actually depends, or it is also the sum of powers of the concentration terms in the rate law. So this is nothing but what we can say the order of a reaction. And students, we know that the concentration of the particular that reactants may change, and this due to this change in concentration, some factors will also affect on the rate of that reaction. So the order will depends on the situation of that reaction and the concentrations which are present in it. It will change according to the concentration terms. Now students, coming to the next point, molecularity of a reaction cannot be zero, though it is a number, but it cannot be a zero, and it will start from a single reactant and its value will be minimum of 1 but not 0. And if you consider the order of a reaction, sometimes concentration of a particular that reactant may be 0, so the order of reaction can be 0 sometimes, and we already seen zero order reactions in examples. Coming to the next point, it is a theoretical concept, means by observing that reaction we can write its molecularity, but order I already explained, it is determined experimentally because the concentration terms are very important while deciding the order of that particular reaction. The next point, it is always a whole number, and if we consider the order of a reaction, it can even have a fractional values too. Means sometimes the order of a particular reaction may be 3.2, 3.5 like this, means it may be a fractional value. The overall molecularity of a complex reaction has no significance. Individual step has its own molecularity. Means if we consider a particular reaction in a number of steps, while calculating the molecularity, each step decides its molecularity. Means it will depends on individual method. Means individual step can have a individual molecularity, but order is different from that. Order of a reaction is for overall reaction, though it is having in number of steps, but order of a reaction is for overall reaction. Now students, coming to the next point, integrated rate equations. In that we will choose zero order reactions first. Now zero order reactions means what? Zero order reactions means that the rate of a reaction is proportional to 0 power of the concentration of reactants, means their concentration may be 0. Now this simple elementary reaction we are considering here, reactant gives product, that is R gives P, For that, we are going to write the first rate law. It will be minus d by dt of concentration of R, and if we calculate its rate constant, that is k, by remaining to the proportionality sign, we can take here k, and we have already taken here k concentration of reactant raised to 0. This raised to 0, this term indicates its concentration. As the quantity raised to power 0 is unity, in that case its value becomes 1. So what will remain is nothing but minus d by dt of concentration of R is equal to k. So by rearranging, we can write d concentration of R is equal to minus k into dt. Now students, in the next slide we are integrating that above equation on both sides between the limits. Reactant has initial concentration 0, so here the lower limit we have taken is R0, and the upper limit is we are taking R, and time also has initial time as well as the time at which we are going to calculate the rate of that reaction, so its limits will be 0 to t. So we have integrated the above equation, so we will get this term, and after applying limits to that particular equation, we are doing the next procedure for it. So the integrating of that particular term will leads into this equation, that is upper limit minus lower limit. So R concentration of R minus R0 will get here is equal to minus k into t. Integration of differentiation of any term will get cancelled here according to the integration rule, and we will get the term t here. So the final equation will becomes like this: concentration of R minus concentration of R0 is equal to minus kt, or we can also write that equation like this by changing the minus sign of both sides. Now we can also write in terms of k also this equation. So what is the term we are getting here? Concentration of R0 minus concentration of R divided by t, because t we have taken at the other side of this equation. Now friends, we are going to plot a graph for a particular zero order reaction. Now variation in the concentration versus time plot we have plotted here in this figure. You will notice here concentration of reactant versus time. Concentration is we have taken on y axis and time on x axis, and the slope we are getting is nothing but the negative slope. So this is the plot for that zero order reaction. Now students, the next thing in this chapter is very important, and the number of problems may be asked on this first order reactions. So we are also going to look a integrated rate equation for first order reactions. Now students, according to the previous zero order reactions, the same things are also we are doing here. First order reactions means that the rate of reaction is proportional to the first power of the concentration of reactants. So for understanding, we are considering the simplest reaction. R gives P, in the sense reactants are converting into the product, and corresponding rate law we have written here, and by doing rearrangement, concentration of R term at the right hand side of the equation we have taken at the left hand side. At the same time, dt we have taken at the right hand side of the equation. Now by manually we are doing the integration for the integrating the above equation in between the limits R0 to R and time in between 0 to t. So on integration we are getting the terms like this: log of concentration of R minus log of concentration of R0, and here after doing integration also we have applied the limits to the above equation, so we will get this equation is equal to minus k into t, or we can also write that above equation like this, that is log of R0 minus log of R by removing the minus sign of k at the right hand side. So if you want to write that equation in terms of kt, we can also write like this: kt is equal to log of r0 upon r, or we can also write like this by taking the t at the right hand side of the equation. So it will becomes 1 upon t log of r0 upon r. So this is the equation when we are taking that natural log into the log to the base 10, because the number of problems we have to solve in terms of by taking the help of log to the base 10 log table. So this is the required equation what we have to use at the while the calculating the k, that is order of that particular reaction, and the time, sometimes time also you have to calculate. So this is the final equation for calculating time as well as the order of that particular reaction. Or sometimes in problems, initial concentration of reactant or product at time t can also be calculated by using this equation. Now this 2.303 value is we have taken while converting that natural log into the log to the base 10. We have to multiply it with this value 2.303. So this is the equation of first order rate equation. Now in our next lecture we are going to calculate the integrated rate equations for second, and number of equations can be also calculated for different type of reactions. So this is the plot for the first order integrated rate equation. Log to the base 10 of r, concentration of r0 divided by r, we have plotted on the y-axis versus time, and the slope we are getting is nothing but k divided by 2.303. and this equation we have to assume, we have to imagine in terms of y is equal to mx plus c. So the equation we are getting here in the form of y is equal to mx plus c. So y term is nothing but the this log to the base 10 of r0 upon concentration of r0 upon r, and the x term we are getting when we imagine that equation in terms of y is equal to mx plus c, x we are getting in terms of time. So the graph will be having a nature of straight line passing through origin. So this is the nature of graph what we are getting after the end of integrated rate equation. Now half life of reaction we will see in our next lecture. Thank you very much.